Let's start with a simple question. In 112 gig or 224 gig system, where everything adapts continuously, why we intentionally freeze the CTLE after training? That sounds simple, but here's the reality. Switching resistor or capacitors in a left continuous time signal path inject charge, shift bias point, and move pole instantly. In painful systems, the small analog disturbance can ripple into slicer error, DFV confusion, or even CDI instability. So the real question isn't why not adapt, it's can we design the CTLE stable enough that it doesn't need background adaptation at all? When you flip a capacitor back or change a rejection resistor, you don't gently move a pole, you jump it. That creates an impedance discontinuity and a tension in the signal path. At 112 gig painful, even a short tension can produce a burst of errors. The slicer sees garbage. The DFE update on the bad data. The CDR phase detector got confused. So, freezing the CTLE isn't laziness. It's often a deliberate or intentional system stability decision. Once we accept that CTLE may be trained once and freeze, the mindset changes completely. We cannot rely on digital logic to fix analog drift later. That means margin must be designed in upfront. We must budget for the process variation, temperature drift, aging, supply ripple, and modeling error before tape out. A good frozen CTLE isn't one perfect response curve at typical conditions. It's a family of curves that remains acceptable at worst-case sequence. The high-frequency behavior of a source distribution CTLE depends on GM directly, and GM depends on mobility and bias current. As temperature rises, mobility drops roughly with T to the minus 1.5 power. If your bias current stays constant, GM falls. When the GM falls, the DC gain drops and the high-frequency pole shifts lower. Your peaking shrinks, your eye closes. So, if we want a frozen CTLE to survive temperature, we must stabilize GM itself. So, what can we do? Think about the compensation images for 5 seconds. Bingo! The fix is conceptually simple. If mobility decreases with the temperature, we increase the current with the temperature. If ID scales roughly with a T to the 1.5 power, GM becomes approximately constant across temperature. That keeps both DC gain and the critical high-frequency pole stable without flipping any digital switches. Instead of reaching to drift later, we prevent it at the source. This is how you freeze a CTLE the right way, by stabilizing transistor operating point, not adding more logic. A nominal corner, aggressive high Q peaking can produce a beautiful eye, but that same setting becomes brittle at corners. A slight shift in GM over channel loss, and now you are amplifying noise instead of a signal. For frozen CTLE, choose a slightly conservative peaking profile. Leave some equalization for DSP. The goal isn't maximize I at TT. It's stable I at SS hard with a VDD droop. A strong architectural trick is separating coarse frequency shaping from broadband trim. One knob select among stable pole 0 profile. Another trims overgain. This prevents fragile ultra-fine capacitor banks and reduces sensitivity into parasites. It also makes training more robust. because you are not relying on extreme fine pore placement to survive process and temperature variation. With CTLE frozen, distortion cannot be corrected later. Noise can sometimes be averaged. Distortion cannot. If high-frequency boosts push the outer painful level into compression, you permanently degrade SNDR. So design headroom for the worst-case input amplitude combined with worst-case peaking. Frozen CTLE means linearity is not negotiable. A frozen CTLE must also reject supply ripple. If a bias nodes are sensitive to VDD noise, GM get modulated. When GM is modulated, the high frequency gain is modulated. That converts low frequency supply ripple into in-band amplitude noise or jitter near nexus. Without background adaptation, you cannot fix that later. Strong PSR and bias isolation are mandatory. The CTLE doesn't operate alone. Its output swing and common mode fits direct into VGA, slicer, and LEC. If temperature drift push swing too high, the next stage compressed. If gain drop too much, dynamic range is wasted. Frozen CTLE design requires strict interface contracts for amplitude and common mode across all corners. Stability at the CTLE output must translate into stability at the system level. Since CTLE tuning happens only during training, the metric matters. Don't just maximize I high. Use SNR, histogram separation, or error-based metrics that reflect real robustness. Choose the safest setting, login, and let DFE or DSP handle dynamic variation. The CTLE becomes a stable alone preconditioner, not a continuous moving target. Here are the summarized images showing you why CTLE without background adaptation. Because in high-speed continuous time analog stability can be more variable than flexibility. By stabilizing GM with PTAT biasing, choosing conservative peaking, separating shape from gain, guaranteeing linearity, designing for PSR, co-designing interfaces, and validating aggressive across corners, we can build a CTLE that survives real silicon life without touching a digital switch after training. That's not a simple design. That's discipline, analog engineering, and design guarantee. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and place your comments down below. Lastly, please share the video link with the people who may be benefiting from it.